In this video, we're going to talk about solutions and solubility. Before we get into solubility, I'm going to take a few minutes here and review how we measure solution concentration and a few of the different ways that we measure that. That's going to become important later on because in some of our calculations, we will need to calculate solution concentration. So we've done all of these before, but we're going to go ahead and briefly review these, and then we will get into solubility. So we have to have some way to be able to define how much of a certain substance we have in a solution and compare that to an amount of solvent in a way that's concise and that other chemists will know what we're talking about. So we can use quantitative terms like dilute and concentrated to describe something that doesn't have very much solute versus something that has a lot of solute, but that doesn't really give us anything very specific. So the most common way that we measure solution concentration in chemistry is using molarity. So molarity you should be very familiar with at this point. Molarity is the number of moles of solute per liter of solution. So we typically abbreviate that formula, M, which is molarity, is equal to moles over liters. Some of the solution concentrations or ways of measuring solution concentrations that we don't use quite as frequently, but do still get used. One is mass percent, where we look at the mass of solute per mass of solution, or we can sometimes do volume percent, which is volume of solute over volume of solution. Mole fraction is another common way. So we take the mole fraction of whatever component we're talking about, divide it by the total number of moles of whatever components we have. So we can have 2, we can have 3, we can have more than that. But we take the number of moles of whatever component we're interested in and we divide that by the total number of moles. And finally, molality, which we use occasionally, is moles of solute per kilogram of solvent. So sometimes that gets abbreviated. Lowercase m is equal to moles, and we know it's moles of solute over a kilogram of solvent. So now that we reviewed solution concentrations, let's talk about solubility. So solubility is the maximum concentration of solute that can be dissolved. Even something that's highly soluble like sodium chloride in water is going to have a limit to how much you can dissolve. If you continue adding salt into water, you're eventually going to reach a point where no more of it dissolves, and you're going to start getting a bunch of salt at the bottom of your container. Because no matter how soluble something is, there's going to be a limit, a point at which the solvent can no longer hold any more solute. So solubility is how much of a particular solute we can dissolve in any given solvent. So a few terms that we use related to solubility. When a solute's concentration is equal to its solubility, we call the solution saturated. So in other words, the solution is holding as much of the solute as it can. If the concentration of the solution is less than what we can dissolve, meaning that we have less of the solute in the solvent than we could have, we call the solution unsaturated. So we could put more solute in, but we just don't. And sometimes we don't need a solution to be saturated. When the solute's concentration is greater than what we can normally dissolve in the solution, we call that supersaturated. So there are ways to make a solution supersaturated. if we heat a solution up, we can sometimes get more solute to dissolve. But if we cool that solution back down, the solute doesn't precipitate out immediately. So for a period of time, that solution is super saturated because we've got more dissolved than what should be in the solvent at that particular temperature. Eventually, if you let the solution sit long enough, you will start to see some precipitation at the bottom. But for a period of time, the solution is going to be super saturated because it's got more solute than it should have. So the extent to which a solute will dissolve depends on several things. One is the nature of the solute and the solvent molecules and how they interact. So we've talked about things like polar solvent or polar solutes dissolve in polar solvents, non-polar solutes dissolve in non-polar solvents. So we have to look at the polarity and the intermolecular forces, the temperature at which the solution is formed. For a lot of ionic compounds, the higher the temperature, the more will dissolve in a given solvent. There are exceptions to that, but generally, when we're dealing with ionic compounds, we can increase solubility by increasing temperature. For gaseous compounds, it's actually the opposite. Gases actually dissolve better at colder temperatures, which we're going to talk about a little bit more just a little bit later. And the other thing we have to think about when we're dealing with gaseous solute is that the pressure is also important. So how much pressure we're putting on the gas, or how much pressure the gas is under, dictates some of its solubility. So we mentioned most ionic compounds will increase their solubility with temperature. Like I said, there are some exceptions to that, but for the most part, the majority will increase their solubility with temperature. But gases tend to be more soluble at a lower temperature. So if you think about something like a soda, if you leave your soda in the refrigerator, then typically it stays carbonated and it stays like you like it. But what if you leave your soda sitting in a warm car for a few hours and then you come back? What usually happens to your soda? Well, usually your soda's flat at that point because carbon dioxide is not very soluble at high temperature. So eventually it's going to leak out of your soda bottle and you're going to come back to just the water and whatever flavoring is in your soda. So there's actually a law or an equation that shows us the pressure dependence of a gas. So Henry's law tells us that the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. So the amount of the gas is measured in its concentration, which in this case is molarity, or moles per liter, which is the same thing as molarity. K is the Henry's law constant, and that constant is going to be the same for a particular gas. So for example, there's a Henry's law constant for CO2, there's a Henry's law constant for O2, there's a Henry's law constant for N2, and so on. So the constant will be different for different gases, but it will always be the same for the same gas. And P is the partial pressure of the gaseous solute above the solution. So let's take a look at a problem and see how this works. A certain soft drink is bottled so that a bottle at 25 degrees Celsius contains carbon dioxide gas at a pressure of 5 atm over the liquid. Assuming that the partial pressure of CO2 in the atmosphere is 4.0 times 10 to the negative fourth atm, calculate the equilibrium concentrations of CO2 in the soda bottle, both before and after the bottle is opened. And then we're given the Henry's law constant for CO2 in aqueous solution. So, let's take a look at this. Before we open the bottle, we have the carbon dioxide under partial pressure of 5 atm. So we're told that the concentration is equal to the Henry's law constant times the partial pressure. And we're given Henry's law constant of 3.1 times 10 to the negative 2 moles per liter. And so that's moles per liter times atm for the Henry's law constant. And we have a partial pressure of 5 atm. So if we multiply this out, so atm cancels with atm. If we multiply 3.1 times 10 to the negative 2 times 5, that gives us 0.16 moles per liter, and moles per liter is the same thing as molar, so 0.16 molar. Now, what about after we open the bottle? So the concentration is equal to the Henry's law constant times the pressure. So the Henry's law constant doesn't change. We're still dealing with the same gas and still at the same temperature. But now we have a partial pressure of 4.0 times 10 to the negative fourth atm. So if we multiply 3.1 times 10 to the negative 2 times 4.0 times 10 to the negative 4, we come up with 1.2 times 10 to the negative fifth molar. So we can see even after we open the soda, the concentration of carbon dioxide drops pretty dramatically here. We go from 0.16 to 1.2 times 10 to the negative fifth. So we will get some more practice with Henry's law in class, and I will see you in class.